random projective. Okay, so some of you may have heard of what projective geometry is, but let's see what it is. So first, we're not going to be working with the Euclidean plane. In the Euclidean plane, like these two lines that are there, they're just like parallel. They don't intersect. Like any other line you would have picked does intersect this line, but there's this one exception of parallel lines. So, and like you can see, I've just picked like 3 random examples of problems where you're asked to show that things are like concurrent or they're all parallel, which is just like an annoying distinction to have to make. So projective geometry fixes this by along every line, like eventually after you go like sufficiently far, there's this extra point which we'll denote by P infinity. It stands for the point at infinity. So this line here, the green line, also has the same direction as the yellow line. So it also eventually meets at like these 2 points at the same, the yellow and the green points. This is also that point, P infinity along this direction. So for this line, this, what is this pink line? There's going to be a different point at infinity there. And this other red line also goes through it. So now we can just say that every line does intersect every other line. We don't have to bother about stuff being parallel. And also this like creates a bunch of points at infinity. We'll just say that all these points at infinity are collinear on a thing that we're going to call the line at infinity. So that's all the differences between the projective plane and the Euclidean plane, which you've probably been working with before. How do you remove stuff? Okay, so let's just begin with the basic definition. So first, what is a cross ratio? And it has like fancy notation. It's written like this. With 8 people. Hello, Neerav. So in this, the lengths that we're going to be taking are going to be directed. So to just give an example of what directed lengths mean, suppose we have A, B, C. We're going to assume that going right, like AB is like positive, BC is positive, but anything going the reverse direction, for example, CA or CB, they're both negative. And we'll see why this is relevant in a while. So the value of this cross ratio, which is written like this, is equal to CA by CB divided by DA by DB. So it's like CA times DB by BC times, oh, I should not mess up. Yeah. CB times DA. So that's what a cross ratio is. And these things can be surprisingly helpful for the following reason. So suppose we pick 4 points on a line. Suppose we have A, B, C, and D. And let's just pick a random point, say X, because why not? Right, so maybe I'll just change the order of these. So actually before this, let's just look at this one thing. We defined this directed length. So we know when something is positive and when something is negative. So in what cases do you have that this cross ratio is positive and when is it negative? Like there are various possible ways these points can occur in a line. You could have just AB, CD. You could have ABCD like this. And you can also have AB and CD like this. So in each of the cases, let's check what is going to be the sign of the cross ratio. We're just going to use this definition. Okay, so for the first one, what is it?
Positive.
Yes. Okay. So a CA is negative times DB, which is also negative. Then CB again negative, and then DA again negative. So the overall thing is positive. And what about this case? The same way, this is also positive. And if we check this case, we have that negative times negative, positive, negative. So this is actually the only case when it's actually negative. So it's negative only if AB and CD are like these segments intersect each other, but one is not contained in the other. For example, in this case, AB and CD, they just don't intersect. And in this case, like this is AB and this is CD. One is contained in the other. So if points occur in this order, the cross ratio is negative. And this is going to be specifically important when we look at harmonic cross ratios. And that's going to be when this cross ratio equals -1. And we'll see that this -1 cross ratio actually comes up in a lot of familiar configurations and can be used to prove a lot of interesting stuff. So right, back to this. The advantage of this is that if you look at these angles that are there, whatever, let's just give them names. Let's say X, Y, Z. I'll change this to P. So we want to express this cross ratio in terms of these angles. And it turns out like you can actually write it in terms of those angles, which turns out to be pretty useful. Because suppose that this cross ratio depended only on these angles, then let's pick something else. Suppose you have another random line and you pick points A dash, C dash, B dash, and D dash. So the advantage is that because this cross ratio only depends on these angles, you're not changing the value of the cross ratio when you're essentially like, it kind of looks like a homothety, but it's not. This is called taking perspectivity at a point. And this is written as this. So you have AB semicolon CD. And when you're taking perspectivity at P, you write it like this. And because this cross ratio only depends on these angles, this cross ratio is going to be equal. And taking perspectivities is going to be very useful. But let's just first prove the fact that this cross ratio only depends on the angles. This is unfortunately just using law of sines like a bunch of times. But like, okay, let's just do it because why not? So we have this. So applying the law of sines in triangle PAC, let's say this angle is theta, 180 minus theta. So we have PA by sine theta is CA by sine X. And similarly, using it in PCB, we have that PB by sine 180 minus theta, which is sine theta. is equal to CB by sine Y. So if we divide these two equations, we get that the value of CA by CB times sine Y by sine X. The sine theta gets cancelled and it's equal to PA by PB. Right. So this gives that CA by CB is sine X over sine Y times PA over PB. And similarly, you get that dA by dB is also like sine something by sine something times PA by PB. And the cross ratio is defined to be like this divided by this. So this PA by PB gets cancelled. And so it only depends on what those angles are over there. So beyond this, we will essentially not use trig much. We'll just use the fact that you can take perspectivity through P. And when you're changing this cross ratio from this line, like in this case, this green line onto this pink line, it's called projecting. So you're projecting through P. So when you project through P, you're sending A to A dash, C to C dash, B to B dash, and D to D dash. And this does not have to be just with lines. You can also do this pretty cool thing that if you have a circle and a point P, say you have points A, B, C, D, and not necessarily a circle. It's also true for a conic, but we won't bother with that. So you can kind of project from a circle onto a line, but only through a point on the circle. This is important. It's like quite easy to forget when you're just projecting stuff. But do remember that if you're projecting through like circle and line, the point through which you're projecting has to be on the circle or conic, whatever. A dash, B dash, C dash, and D dash. So the cross ratio is defined the same way on the circle too. It's still equal to the value of CA by CB divided by DA by DB. And it's actually the exact same. Like you can just repeat law of sines.
We can just then like do it with AD. And then we can just like draw a line AD and we can just then do by the angle perspective that you told.
You can do what?
Like you can draw line AD and just mark those intersection points and show that the cross ratio of those on the circle is equal to the one on the line, and then we can easily project.
Okay, yeah. Okay, you don't have to do it to this line. You can just show that the cross ratio ABCD on this circle is the cross ratio of this AB double dash, C double dash, and D. But essentially the same thing. You need to just do trig. And let's not do like evil stuff during this class. Trig isn't that bad, but still, projective is a lot cleaner than that. And this is just the preliminary results. So that's all we need to know about cross ratios. And for most part, we will be dealing with when the cross ratio equals -1. So, so when you have stuff like this, so what does it mean? In what order should the points lie for the ratio to become -1? Like for the ratio to be negative. As in, let me just place A and B. Where should C and D be? Hello, person who is supposed to take this class. Whatever.
C should lie between A and B, and B should lie beyond B. B.
Yes, it will probably lie around here. So right. So this is kind of how it looks with A and B there, and one of the remaining points between A and B, and one of them beyond B. And what does this cross ratio mean? It simply means that I'm dropping the directed lengths for now. Let's just look at like value of length. We have that AC by CB is equal to AD by BD. That's what the cross ratio condition means. So technically, like whatever ratio this point C is dividing this line in, this point D is also dividing this in that ratio, but externally. And with respect to AB, points C and D, they're called harmonic conjugates. And if it's -1, this is called a harmonic cross ratio. And this is also the reason certain quadrilaterals are called harmonic quadrilaterals. But we'll get to all of that later. Let's just begin with a couple of examples of why we even care about these harmonic cross ratios and why they're relevant. So let's begin with this. There is a triangle ABC. We have 3 concurrent serials like this. And let's say D, no, this is terrible. Some bending. Not E, let's say Z. Okay, so this is a configuration that comes up quite commonly, and most of the times you won't be given that A, D, B, E, C, F are concurrent. It'll just be like kind of well known. Suppose, for example, D, E, F are a feet of altitudes. In that case, you know that A, D, B, E, C, F concur at the orthocenter. And if like they're the in touch points, like where the in circle touches the sides, you know that A, D, B, E, C, F still concur at the Gergon point. And if they're midpoints, then you know that they concur at the central, and so on. So we actually claim that this cross ratio BC BZ is equal to -1. So it's in the correct order. One of D and Z is between B and C, and one is outside. So we really just want to show that this BD by DC is equal to BZ by CZ. Okay, so how do we do that? Like, what is a theorem that involves ratios such as this, especially when you have concurrent something?
We can use theorem and loss.
Yes, so because they're concurrent, we have that by Siva's theorem, BD by DC times CE by EA times AF by BF is equal to 1. But also EFZ are collinear and they lie on corresponding sides. So by Menelaus, we also have that BZ by CZ times CE by EA times
The same
AF
kind
by
of
BF.
the same kind of pairs only.
Yeah, and these pairs here, they're repeating. So we have that BD by DC is these two things are actually equal, which is what we wanted to show. And in fact, we didn't even need to like observe one is on, because Menelaus actually gives that if you take lengths to be directed, this is -1. So when you divide, you actually get the cross ratio like exactly minus with the sign.
And like try to get a purely projective solution.
Can you get a what?
Purely projective solution.
Purely projective condition for?
like this to happen. Like we show that if BC dz is equal to -1, BC dz is equal to BDCZ. Like we can just try to project from point A, then we can try projecting from point B.
What? Oh, you mean, yes. So because we have this cross ratio to be something nice, we can also look for what other cross ratios are nice. So let's just introduce point names X and Y, say. So yeah, just pick a point that you want to project this cross ratio from. And like most points will probably just work. But yes, as Anurag said, we can project through, say, F. So suppose we're projecting this, different color. Suppose we're projecting this through F. Which line do you want to project it onto? Or like, suppose you're projecting B through F. Where would you want to project it to? Like what other point lies on FB? So it's A. So through F, when you're projecting, B gets sent to A. And we're actually projecting onto this line AD here. So we can send Z to X. And we send C to Y. And we leave D as it is. So this in fact gives us that AY dx or xt, whatever, is also harmonic. This is also equal to -1. And we projected through F. You could have got the same thing by projecting through E. And suppose you project it through A instead. Where can you send B to? You can send it to F. C goes to E. D goes to X. And let's leave Z as it is. So we in fact have these four things, F, E, X, Z. This is also harmonic. We also have that AY dx. This is also harmonic. So let's, in this kind of configuration, this comes up
Then we
like
can
very
like try projecting from Y and get that AY dx is the cross ratio of BC dz is equal to the cross ratio of BDCZ, which is just like in 1 upon that, not considering the directed length. Then we would like get BC dz is equal to 1, not considering directed length, and we can do that position argument.
Wait, what are you saying? Okay, you mean that instead of projecting through A, you can also project through Y?
No,
And
like we projected from A to the line ZE. And now we can just like flip the points in the cross ratio to just get that 1 upon that cross ratio is equal to 1, not considering directed lengths at all.
yeah, so yeah, if you project this through E, then B goes to, no, projecting through Y. Then this goes to E, C goes to F, D goes to X, and this goes to Z as it is. So yeah, E and F, just you can flip them and it does not matter. And also, usually the sign of the cross ratio is mostly relevant. But just in case, if you have a cross ratio A, B, C, D, if you swap A and B, it's still equal. And if you swap C and D, it doesn't matter. What matters is if you swap B and C, say, like you can think of the semicolon as separating these two. If you swap things on one side, it doesn't matter. But if you swap, like say B and C, then the cross ratio gets negated. So the cross ratio ACBD would actually just be 1. and not -1. Okay, right. So next, okay, this is also a very common place where harmonic stuff comes. So let's do this. You have this 90-degree angle. And you have this. Right. Bad diagram, but whatever. And suppose you have these two angles are equal. So if you have this 90-degree and equal angles, then also we have that this cross ratio is equal to -1. And you can do this synthetically, but okay, let's just not bother. Like suppose this angle is x, then this is 90 minus x. And so you can just like, BC by CD. This is P. Like this is the angle bisector, so it's just equal to PB by PD. And you know that BA by AD, because sine 90 minus x and sine 90 plus x are also equal, they are to 180. So that also you get is equal to PB by PD. So you actually get that this cross ratio AC BD is equal to -1. Yes, okay. This is not really bash, like angle bisector theorem, come up. It can be proved synthetically, which is okay, let's not go into that. But angle bisector theorem is synthetic. Sine thing, fine. You can do similar triangles and stuff, but let's not bother. Okay, so do you all know what inversion is? Like, if not, I'll just simply explain what it
Yes,
is.
yes. You can just create a poll.
Fine. Your watch is like no one actually responds to this.
People do respond to poll.
Let's
I've seen this.
Yeah. Yes. Okay. Respond to the poll. This is
You
probably
forgot to
random.
launch it. You have to
What?
launch it.
No.
You have to launch the poll.
Scam.
No, don't create it. You have just like already created it. Cancel
Yeah.
it and just click on this. Click on the third through
What?
how to launch it.
Never mind. How are you supposed to launch this?
Ask Nana.
So Nana, how are you supposed to launch this?
Click on it. Just click.
I am clicking on it. Nothing is happening.
You know what? Create a new one. Even I don't know. मेरे को अनुराग help किया था तब.
Oh. Okay. So do I save? Okay. Good.
Huh?
No.
You know what? I know how to create it. Just
No,
give me
we're
some
not doing a poll. Just answer. So Nana, do you know what inversion is?
Yes.
Anurag, do you know what inversion is?
Yes, yes. I guess
Devayu, do you know
almost
what
all.
inversion is?
What is inversion?
Oh no. Okay, fine. We'll actually just define inversion just in case. So we actually won't be needing any of the fancy things in inversion, like circle passing through centers, inversion goes to line. It's too much fanciness. We'll just do the definition of inversion. Suppose you have this circle O, let's say radius R, and you pick random point, say P. So its inverse, which we'll denote by P dash, is defined to be the point along ray OP such that OP times OP dash is equal to R square. And okay, that's all we're going to do about inversion. So suppose like this is the point P, right? So we're going to draw a line that's perpendicular to OP that intersects it at its inverse. And this line we're going to call as the polar of P. And if you're given a line, then let's call this line L, then this is called the pole of
It was what is this line L defined to be?
L is just a random line. So then you like drop the foot onto that line and then take its inverse. Like essentially just reversing what we did here.
Okay.
And pole and polar are easy to get confused. Just like easy way to remember is that points are smaller than lines and pole is smaller than polar. So pole is like the smaller word. It refers to a point and polar refers to a line. So, okay, why are poles and polars relevant? So there is this theorem called Lahir's theorem. I don't know how to pronounce it, so I apologize. It states that suppose point Q lies on polar of P if and only if P lies on the polar of Q. So, okay, well, how are we going to prove this? So what does it mean for P to lie on the polar of Q? So we're going to take the inverse of Q.
It means like P is the inverse of Q.
What? No. P lies on the polar of Q. P is not
Okay.
necessarily then. So
Yes.
this line here is going to be the polar of Q, if this is Q dash. And this is 90 degrees. So essentially, let's introduce P dash also. So you want to show that angle PQ dash Q is 90. How are we going to do that? The only definition allowed to use of inversion is this, nothing else.
You can just like then take those that similar triangle thing. That angle OQP is equal to angle OP dash Q.
Why?
Because like they are similar.
Why are they similar?
Because like OP into OP dash is equal to OQ dash into OQ.
Yes, so an easier way to say is OP into OP dash is R square, which is OQ into OQ dash. So this quadrilateral is cyclic. So if this angle is 90, this angle is also 90. So this means that this green line, let's call this L2, L1. So if Q lies on L1, then P lies on the polar of Q, which is L2. So that's all there is to this theorem. So, okay, let's now come to quite a famous theorem. Suppose you have a cyclic quadrilateral, say ABCD, that looks like this. And now we'll draw all possible diagonals. Explain the inside. Let's say E. Let's say this is P, this is Q, and this intersection is called R. And let's say the center of our circle is O. So the claim is that this triangle PQR is what we call self-polar. So this means that the polar of Q is PR, the polar of R is PQ, and the polar of P is QR. So essentially, the polar of every vertex is the side opposite to it, and every side's pole is the vertex opposite to it. So it's like some nice sort of symmetry. And what is a consequence of this? So what does it mean if, like, what property of polar and pole do we know? Like, in relation to the center of the circle? If you just have
OQ perpendicular PR.
Yes. So this means that supposing we had that self-polar thing, we have that PR is perpendicular to this. And if you draw this, QR is perpendicular, and similarly, OR is also perpendicular. And what does this mean?
R is the orthocenter of the triangle PQ.
Yes, or you could also, like, to maintain symmetry, you can say that O is orthocenter
Yes. Okay.
of PQR. Yeah, it doesn't matter because R is also the orthocenter of POQ. And it's more obvious because we're used to looking at orthocenters inside a triangle.
Yes, yes.
So this is a pretty cool result because supposing you didn't have any of the polar stuff, you're just saying that you take this random quadrilateral and find its diagonal intersections, and then suddenly you have that O is the orthocenter of this, which seems pretty random and also cool. So let's try to prove this. So if we just do it for one thing, by symmetry, it holds for the other things. So let's try and show that R is the pole. I mean, okay, let's show that PQ is polar of R. And by symmetry, the other things will actually because it is important. Okay, so the way we're going to do this is actually by showing that individually P lies on the polar of R. And then we'll show that Q lies on polar of R, and they're both analogous. So let's just do it for one of them. So suppose we want to show that P lies on the polar of R. By what we just did, what does that mean?
It means like then R lies on the polar of P.
It means that?
It means R lies on the polar of P if P does lies on the polar of R.
Yes, it does mean that. So
like if you prove it for only one line, then you would be done.
yeah, so we just want to show that R is on polar of P, which is the same. So really just want to do it for any one of these. So any ideas? How are we going to do this? Let's just add in a bunch of intersections and stuff. So if you look at this triangle PDC, what have we done above that's like looks very similar to this?
Sigma less.
Yes. Okay, yes, I should mention that theorem that we proved because we use Siva and Menelaus, it's called as Siva Menelaus. Yeah, so I'll label things. Let's say X and let's say this is Y. So what does Siva Menelaus tell us? Like just any of the results, they're all equivalent.
Like the cross ratio of QR DC is equal to -1.
Yes, so we have that cross ratio QY DC is actually equal to -1. And oh, okay. Just a minute, I'll be back. Okay, I'm sorry, but the Wi-Fi needs to be switched off in my house for a minute apparently. So just like think about this for a minute, I guess. Soon enough, my Wi-Fi will die. I'll rejoin after a minute.
No problem.
I should make someone else host. Okay, so essentially, right. So for the problem that we were doing, essentially we'll use this cross ratio to actually show that the point R lies on the polar of P. So yeah, can you all see the screen?
Yes.
Yeah.
Nice. So we want to show that R lies on the polar. So what is, before we do this, we should actually just look at what a polar means. So another property that we have was O, P, and you have P dash somewhere. So we actually let's suppose P is outside the circle. And then this polar that's there, suppose it intersects it at say X and Y. Then we actually have that Px is tangent to the circle. Do you see why?
Yes, due to the similarity.
Hmm?
Due to the similarity of like OPX and OP dash. Like,
Yes. So okay, let's not do Y because Y is done.
yes.
So we know that OP dash into OP is OX square. So this means OP dash by OX is OX by OP. So we get that triangles OXP and triangles OP dash X are similar. And so this, since this is 90, this is also 90. So we indeed have that PX is a tangent. So what we're actually going to do here is the point R is kind of weird to deal with. So we'll instead just show that, sorry, what am I saying? Yeah, okay. We should actually do this with Q in order to be able to see this in this with what I've drawn. Right. So suppose we want to show that R is on the polar of Q, we want to show that this line is the polar. Or in other words, we want to show that these points X and Y, they lie on the polar. So by what we just saw, we want to show that if like tangents exist like this, let's say M and N, we want to show that that coincides with this actually. So we haven't done harmonic quadrilaterals yet. Maybe I'll do that first.
Wait, we can do one way. Can you just tell if it's correct or not? Like you can then get that by saying that the cross ratio of QIDC is equal to -1.
Yeah.
Right. And then we can get that the cross ratio of QXAB is equal to QXAB is equal to like
is also -1.
Then we can do that perpendicular thing to get that X is like perpendicular to PQ.
What perpendicular thing? There are no perpendiculars in this diagram.
We got that angle bisector and perpendicular theorem before, right?
Yeah, that theorem is true, but there are no angle bisectors here, right? How are you going to use it?
Oh, is it an if and only if condition or only if condition?
So the way that yes. So the way this is usually written is that there are three conditions. First one is ACBD is -1. Then we have angle APC is 90 degree. And we have that angle BPC is equal to angle CPD. So if any two of these are true, then it implies third is also true. But if you have like only one of them is true, then that's not enough to imply anything. It's like you need two of these conditions. So you either need a 90 degree or an angle bisector, which in this case we don't have.
Yes. There can exist some configuration issues.
Yeah. So we're supposed to look at what is called a harmonic quadrilateral. Let's say I'm changing the order so it's easier to see. But you have this. P. So you pick 4 points A, B, C, D, and you draw the tangents to the circle at C and D. And suppose they intersect at P, and like suppose PAB are collinear, then we say that this quadrilateral ABCD is harmonic. And it means exactly what you would expect it means, that AC by CB is equal to AD by D. And like the cross ratio of ABCD is actually -1. So, okay, suppose this is true, what can we do? So earlier we looked at projecting from a circle to a line, right? We said, suppose you have 4 points here and you send it here and here. And that's all fine. But suppose one of those points is actually here. Then where does this point go to? It just goes to like
it
this
goes
point
to itself.
Itself?
Oh, no.
No, like I'm projecting onto this line through P. So
Okay.
the closer and closer you take it, it actually ends up becoming almost this line, which is the tangent. So if you want to project P through P itself, it actually just becomes the tangent. So actually, if you try and project this ABCD through, say, point C. So if you're projecting through C, you can leave A as it is. We're projecting onto the line PAB. To this thing. The point B also stays as it is. And C, because it's tangent, it goes to P. And D comes to this point, let's say E. So this actually gives us the following fact that if AB EP is some harmonic cross ratio, then E lies on the polar of P, because the polar of P, as we just saw, is you draw tangents and draw the line.
CD itself.
Yeah. So it's pretty cool actually that you don't care about which circle you draw. You could draw like this circle also. Like we don't really care about C and D. But even now, if you draw tangents, it will go through E. So irrespective of which circle you pick going through A and B, the polar is still going to go through E. Does that make sense? I will assume it does make sense. So in this case, we have that Qy dc is actually equal to -1. And we have a circle going through C and D. So what can we say? By what we just proved.
You can say that A, B, C, D is an harmonic chord.
What? No.
No. Like Q is the intersection of those tangents.
Yes.
Like if you continue XY, then M and N lie on that XY.
Yes. So we can just instead say that Y lies on the polar of Q. Right?
Exactly.
And we also know that PXAB is also -1 by just projecting this thing up.
Like then we get that the polar of P lies on a polar of Q lies on PR. Because like XY and Q are coincident.
Yeah, so we also get X lies on polar of Q. So in fact, the polar of Q must be this line XY.
Yes.
And this line XY is this line PR. So we have that. We have that like this directly. PR is the polar of Q. Does that make sense? And this is called Brocard's theorem. I'm not sure if it's a K or a C, but not sure. Okay, so now let's do a couple of problems. Or okay, let's just do a simple one to start off with. You have triangle ABC. Not much of a triangle with bent sides, but you get the point. We have an N circle. Once again, we will pretend this is an N circle. And you drop the perpendicular onto this, say point X. Sorry. Good. Prove that these two angles are equal.
Can you extend the AF and let it intersect at BC?
Sorry?
Can you extend DF and let it intersect at BC?
Okay.
Then like if we show that YBDC is an harmonic bundle, then we will be done.
Yes. So by the lemma that we did with angle bisectors and harmonic conjugate, we know that if we can prove that cross ratio BC dy is -1, then we can get this angle bisector thing. So this point X is actually not relevant. We just want to show this. And how would we do this? Now we use another configuration that we looked at.
I think it's Broca's theorem here.
Broca? No, I don't think that's useful here.
Okay.
Okay, maybe
We
it
can
would help.
use Sivam in also.
Yes, so AD, BE, and CF concur
And
We
at
need
the
to show
German
that
point.
CDY is harmonic. Cross ratio
We need to show that.
What is the problem?
Oh, the problem was if you drop the foot onto this, then you want to show that this angle is equal to this angle.
Oh.
So we had 90-degree and so we want to show harmonic, so then we'll get angle bisector.
Yeah.
So we just want to show that this is because these concur by Siva-Menelaus, we actually have this. Does that make sense? And okay, you don't need to know that the concur at one point. You just know that BD by DC is whatever S minus B by S minus C, and if you sum cyclically, it's 1. So they do concur. So okay, that's done with this problem. This was Elmo shortlist 2012, I think. Okay, what next? Let me find problems. Okay, so let's do this. Once again, you have triangle ABC. And once again, we have an encircle. There's a lot of these encircles. Touch. Okay, one day I will be able to draw encircles properly like that. But until then. So suppose the end center is I, and we have this point to be some X. Prove that IX is perpendicular to AD.
I mean, this is like the same last thing.
What thing?
Like we have AIDs collinear. Okay.
No, AID is not collinear. Like
How it
ID is
isn't?
perpendicular. It goes like this.
Wait, AID. What is an incenter defined to be? It is like defined to be the intersection of AD, CF, and BE. So
No,
AI
its center is the center of the encircle. ADBCF concur at the Gorgon point. That is a different point.
Oh,
It doesn't.
Okay. Can I say?
Go on.
Let AD intersect
xe at y,
X what at Y?
xe,
XE. Oh, that's okay, fine.
then x d v c are -1 and x y f e is -1,
Yes.
and so like ad is the and d is like the tangent point. So then ad must be the polar of x.
Yes. So as he said, if you project through A, you get X, Y, F, E is -1. So because this is a circle going through E and F, we know that Y lies on the polar of X. But we know that D lies on the polar of X because it's the tangency point. So this line AD is actually the polar. So this means that it is just perpendicular to X. And that's it. Because the polar is perpendicular to the line joining center of circle and the pole. Does that make sense? People actually react. I did not. Okay, fine. So, okay, also an important thing, like it's kind of obvious, but just good to know. What is this cross ratio where M is midpoint of AB? M, and this at like infinity, we have point at infinity.
-1.
Yeah, so because MA by MB is just 1, and P infinity A and P infinity B just becomes 1, because like at infinite distance, they're essentially just the same length. So this is actually just -1. So this is quite a useful thing to keep in mind. Okay, let's do this.
This can be also proven by that midpoint. Like you take that savings to be the medians, and you can then just prove that at the point where BC and the line parallel to BC intersect has this cross ratio is equal to -1, and
Yes.
they do intersect at P infinity.
Yeah, so if you had medians, say DEF, where these are midpoints of sides, then we know that EF, this is ABC, we know that EF intersection BC, and then BCD and that point are harmonic, but these are parallel, so they meet at the point at infinity. So that's what we get, that midpoint and the point at infinity are harmonic conjugates. So, okay, this, what's the statement? I think it's this, let's see. So we'll take 4 points P, Q, R, S. So M is midpoint of AB. Prove that MX is equal to MY. This is called butterfly theorem because this looks like the wings of a butterfly.
So if we prove that the cross ratio of AY XB is equal to -1, then we will be done.
If we prove the cross ratio of what?
AY XB is equal to -1.
Ay x b is why is it -1?
Like then we will get that BXY. Then we do AY.
Like assume it was -1.
Mm,
Then we have xa by xy is equal to ba by by.
yes.
And xa and
Wait,
by,
and B. Okay. Yes.
it's not equal.
Mm. Like we can project AMXY to BMXY.
We can project what?
We can project like AMXY to BMXY.
Yes. So yeah, the idea is to show that the cross ratio AMXY is equal to the cross ratio BM by X. And okay, so how would we do this question? No, I don't think you can prove this that easily. Like essentially to work with cross ratios, you want to be able to project. And we have like PQRS are like 4 very nice points to project from. And you can see that none of them is connected to both X and Y. So you want to work with something that, suppose you want to project through P, you want to work with X and M. So let's instead look at AMXB. Like also in general for problems, if you're trying to use projective on them, like rather than, sometimes you'll want to know, like you know that some things you want to show are harmonic. So you just try to project it through every point possible. But also sometimes when you know projective has to work, you just look at what nice points exist to project from. And that gives you an idea of what cross ratios you should be considering. So in this case, because P is connected to X and M, you want X and M. And for this line, you just pick A and B. So first we project, say, through P. What do we get?
We get the cross ratio of like the cyclic quadrilateral ASRP.
ASRB, yes. So now is there a point connected to both R and S apart from P?
Q.
Yes, so Q. So no, we don't project through P again. That would not be very useful. So we'll project through Q instead this time. And what does it become?
It does become like B. It becomes AN by B.
Yes. So
Yes.
essentially, like you took this X to S and M to R, and then you brought this here and this here by projecting through Q. So what does this mean? By the definition, we know that this is equal to XA by XM times BM by BA. And on this side, we know that this is YA by YM multiplied by BA by BM. So this cancels. And we get this, that AX by XM is equal to BY by Y. So that means that because like these lengths are equal and X and Y are dividing them the same ratio, we do get that MX and MY are equal. Does that make sense?
Yes.
Okay, nice. Yeah, so, okay, this one is going to have a lot more complicated diagram. So but this is also something that is quite useful. So let me pick these points. Like, it doesn't really matter what order you name them. I'm just picking it for convenience. So this is Pascal's theorem. It states that if A, B, C, D, E, F is a cyclic hexagon, and A, B, C, D, F doesn't mean it has to lie on that order. For example, this random looking thing is also a valid thing. Then it states that you take AB intersection DE, you take BC intersection EF, and you take CD intersection AF. So AB intersection DE, this wrong colors.
You want to say that these 3 points are collinear.
Yes, you want to show that these 3 points are collinear. Let's say X, Y, and Z. And Pascal's theorem also works if you can repeat vertices. For example, you can replace B with just A everywhere, and it's still valid. And in that case, AA means the tangent at A to the circle. And it holds in any configuration, doesn't have to look like this. I just picked this because it's easy to see. Like all points are easily visible, which is good. So, okay, just think about it for a minute. I'll be back. Okay, hello. So any ideas? So, okay, let's instead think of this as, instead of trying to show that Z is like there, we'll instead try to show that CB, EF, and XY are concurrent. And actually, to do this, we'll have to add in these new points, say M and N. So we're going to say, suppose this point is there, say Z1 is where BC intersects this line M. Then we're going to show that EF, suppose EF intersects it at Z2. We just want to show some cross ratio involving Z1 and Z2 is going to be the same, because that would imply the points are also the same. So since we're going to end up projecting onto this circle, let's pick M Z1, Y, and N. Because suppose I want to project through C first, so I definitely want to keep Y and Z1. And because I'm projecting onto the circle, might as well keep M and N. And that's the only reason they've been introduced also. So this cross ratio, suppose we project through C, M stays on the circle, Z1 goes to B, Y goes to D, and N stays where it is. So what?
Then note we can take MBDN to MCEN.
MCEN.
Yes, because like there is lambda circle.
Wait, how do you take this to MCEN?
We're projecting through point E. No.
Or if you project through point E, then like B does not go to C.
Yes.
Wait, okay, actually, let's project through point E, because why not? Let's project onto this line and say this point is
Like introducing more points would be
P. So we'll project through E onto this line. M stays where it is. B goes to P. D went to X, and N stays where it is. Now we want to involve something using P and X. So now we'll project through B. Just like a lot of projections. P gets sent to E. X gets sent to A. And we realize this cross ratio is very, wait, okay, fine. Now,
was this intended at all?
no, it's just coincidental. So now we want something involving E and A, so we project through F. M stays where it is, E goes to Z2, A goes to Y, and N stays where it is. So we showed that MZ1YN is equal to MZ2YN. And therefore this implies that Z1 is equal to Z2.
Yes.
Yeah, and that is it. Like to prove Pascal's theorem. Does everyone get the proof? Okay, I'll assume you're doing that. So let's do some problems involving Pascal. So let's just begin with this classic one. We have ABC with a circumcircle. Draw tangent and intersect it at BC at a point, say, X. Now draw B tangent, intersect it at Y. Draw C tangent and somewhere. Then intersect at Z. Prove that X, Y, and Z are all collinear. Like, not the best diagram, but we'll have to do. And as I've said, you just have to use Pascal on this. So in most of these cases, you just have a feeling that you want to use Pascal.
Your voice has got low.
Sorry, what?
Your voice went low for a time.
Okay. Now is it better?
Yes, it is.
Okay, so in these kinds of things where you have a bunch of points in a circle and then intersections in terms of them, you know you want to use Pascal. So in this case, you want to show X, Y, Z are collinear, right? So how would you define X? You want to define it as A tangent intersection BC. So let's just write AA, then something, then BC. So we want A intersection BC, that's X. So next we want, say, Y, which is BB intersection AC. So you just also want it to also be of the form BB blank AC. And the easiest way we can fulfill both of these conditions is just considering this hexagon, AABBCC. This gives us that
They are
AA
all
intersection
cycling.
BC, BB intersection AC, and CC intersection AB, they're collinear, which is exactly what we wanted. This is just XYZ collinear. So let's do a slightly harder example and then we find it. Next. I'll draw a diagram. So you want to show this collinearity. Okay, so any ideas? So,
Using
okay,
Pascal.
yes, we have to use Pascal. So the points that we have on the circle are A, B, C, and D. So let's see if we can define all the points in terms of these. So how would we define P?
P would be the like intersection of double A
Hmm.
with BT.
Yeah.
P
So the
would,
Pascal
yes,
we're looking for is like AA blank, BT blank.
yes.
But the problem is we have nothing along with E. Like CD goes through E, but
We
whatever.
can like we can extend
Yes. So we'll extend
A
A,
dash.
A dash, sure.
Yes.
And
So we
what is
get
a
that,
nice thing? Because these are parallel, this angle is also 90.
yes.
So,
Like
and this angle is 90, so this is actually just a rectangle. So BO, A dash are also collinear. And now suddenly we have like all definitions because now we can define O as BA dash intersection AC, and we can define E as AA dash intersection CD. So how do we fill in the rest of the Pascal?
we have that like AA, like this thing is like a cyclic hexagon. So PO is like
Hmm.
collinear by
No, but
Pascal's theorem.
like how do you, which hexagon are you using Pascal on? Like it's AA something, BD something. What is this something here?
It's ABC, A dash B, A.
Yes, as Boltzmann and Derision said, it's because you want A dash B to be there and also A dash A. So you want to put A dash here, and along with D, you just add C. So what do we get? AA intersection BD, that's B. We have AA dash intersection CD, that's E, and A dash B intersection AC, that is O. So we do indeed just have P, O, and E are collinear as was desired. So also another thing I don't think I mentioned is that Pascal's theorem can be used for any general cone. It doesn't have to be a circle. And that also makes sense because we didn't use any property of a circle over here. We just needed the fact that you can project cross ratios. And as I mentioned, you can also project cross ratios on a conic, so like an ellipse. In fact, most of my circles end up looking like ellipses, but no, this is an actual ellipse. And like you can still do projections and stuff on this. So one advantage is that like for every 3 points, 3 distinct points, there is a unique circle passing through it. So for similarly, for 5 points, there is a unique conic going through it, which is pretty cool. And okay, I'll actually just give this problem and I won't do it. Like you can try it yourself. So I'll just say something about it. That's it. Let's see if I can find it. Okay. Okay, so this problem looks horribly ugly, and I sympathize with you not wanting to do it. It's like you don't want to do it, but it's actually a nice problem. So essentially, another use of Pascal is that in this case, you want to show that some 5 points are cyclic if given like some 4 other points. So what you do is instead also, I don't think I mentioned the converse of Pascal's theorem also holds. If for some hexagon A, B, C, D, E, F, this stuff holds, it means that there is a conic going through those 6 points. So the idea over here is to use Pascal's theorem to show that O, X, Y, Z, P, W, and P. These 6 points you can show lie on a conic using Pascal's theorem, and you'll have to like choose the hexagons for Pascal's carefully. And then the problem actually just follows because 5 points are enough to uniquely determine a conic. So if the conic going through these 5 points, so like these 5 points is a circle, then because O lies on this, we also have that O lies on this circle. And similarly, if we're given that these
See,
5
this like solve the whole problem. Then what is left now?
what? No, this is doing Pascal on this is tricky because, like for example, in the ECMO live solve, like Pranjal said, like let's do Pascal at least 10 times. We did try Pascal, it did not work. So it is tricky to find the correct hexagons to use Pascal on. So all the best doing that. It's like past 10:45. We'll end it here for me.